Welcome to Mech Cosmos, Engineering, Explained. At over 500 kilometers per hour, a supersonic anti-ship missile skims 5 meters above the ocean surface. It is traveling faster than the speed of sound. It has been in flight for less than 2 minutes, and it is heading directly for a warship. The crew of that ship has approximately 30 seconds to detect it, track it, and destroy it before it hits. If they fail, the missile will strike with the kinetic energy of a small car traveling at 500 kilometers per hour, plus the explosive force of its warhead. The result will be catastrophic. The ship will be disabled or destroyed. Crew members will die. The mission will fail. This scenario, the anti-ship missile threat, is the defining engineering challenge of the modern naval destroyer. Everything about the destroyer's design, its weapons, its sensors, its propulsion, and its crew systems is shaped by the need to survive and win in this environment. The destroyer must be able to detect threats at maximum range, track multiple targets, simultaneously engage them with precision weapons, and protect not just itself, but the entire carrier strike group it is assigned to defend. It must do this against threats arriving from multiple directions simultaneously at supersonic speeds from ranges of hundreds of kilometers. And it must do this reliably day and night in any weather condition in any sea state anywhere on Earth. The modern guided missile destroyer is the most capable surface combatant ever built. It can simultaneously defend against aircraft missiles, submarines, and surface ships. It can strike targets hundreds of kilometers inland with cruise missiles. It can provide naval gunfire support to troops ashore. It can conduct anti-submarine warfare hunting and destroying enemy submarines that threaten the fleet. It can intercept ballistic missiles in flight. And it can do all of this while operating independently for months at a time anywhere on Earth with a crew of approximately 280 people living and working in a steel hull 155 meters long. Today we explain everything, how the Aegis combat system integrates every sensor and weapon into a single unified system, how the phased array radar tracks hundreds of targets simultaneously without any moving parts, how the vertical launch system fires missiles in seconds, how the gas turbine propulsion drives 9,000 tons of warship at over 55 kilometers per hour, how the anti-submarine warfare systems hunt submarines at long range, and how all of these systems come together in the most capable surface warship ever built. We are Mech Cosmos. Engineering. Explained. Let us begin. The Arleigh Burke-class guided missile destroyer is the backbone of the United States Navy surface fleet, and the most numerous and capable destroyer class in the world. The ship is 155 meters long and 20 meters wide. It displaces approximately 9,200 tons fully loaded, roughly equivalent to the weight of 6,000 family cars. It is powered by 4 General Electric LM-2500 gas turbine engines, producing a combined output of approximately 75,000 kilowatts. This enormous power drives 2 propeller shafts, giving the ship a maximum speed of over 30 knots, approximately 56 kilometers per hour, and a range of over 8,000 kilometers at cruising speed. The ship carries enough fuel, food, and ammunition to operate independently for extended periods without resupply, making it one of the most self-sufficient surface warships ever built. The gas turbine propulsion system is one of the most impressive engineering aspects of the destroyer. The LM-2500 is a marine derivative of the TF-39 aircraft turbofan engine, essentially a jet engine adapted for ship propulsion. Like an aircraft jet engine, it draws in air, compresses it in a series of compressor stages, combusts fuel in the compressed air, and extracts energy from the hot, expanding exhaust gases through turbine stages. But instead of using that energy to produce thrust directly as in an aircraft engine, the turbine energy drives a shaft that turns the ship's propellers through a large reduction gearbox. The LM-2500 produces approximately 19,000 kilowatts from a package that is remarkably compact and lightweight for its power output. A single LM-2500 engine produces as much power as the engines of approximately 25 large trucks simultaneously. 4 of these engines working together give the Arleigh Burke its extraordinary speed and acceleration. Gas turbines can accelerate from idle to full power in seconds, far faster than diesel engines, which must be warmed up gradually. This rapid response time gives the destroyer exceptional tactical acceleration and maneuverability. In a combat situation where the ship must accelerate rapidly to evade an incoming threat or to reposition for weapons employment, this response time can be critical. The trade-off is fuel consumption. Gas turbines are significantly less fuel efficient than diesel engines, particularly at low power settings. Modern destroyers manage this by operating only 1 or 2 gas turbines at economical cruising speed and bringing all 4 engines online when maximum speed or power is required. The combined gas turbine arrangement allows the ship to match its engine configuration to its power demand, optimizing fuel efficiency across the full range of operating conditions. The defining system of the Arleigh Burke-class destroyer is the Aegis combat system. Aegis is not a single weapon or sensor. It is a fully integrated combat management system that combines radar sensors, weapon weapons, computers, and human operators into a unified whole capable of conducting simultaneous multi-threat engagements automatically with minimal human intervention. The name comes from the shield of Zeus in Greek mythology, a shield that was said to be impenetrable. The implication is that Aegis provides the fleet with impenetrable defense against air and missile attack. Aegis was developed in the 1970s and 1980s at enormous cost, specifically to address the threat of saturation attacks, simultaneous attacks by large numbers of anti-ship missiles launched from aircraft, ships, and submarines that would overwhelm the ability of individual ships to defend themselves using the manual targeting and engagement procedures of older systems. The heart of the Aegis system is the AN-SPY-1 phased array radar. Unlike conventional radar systems that use a rotating dish antenna to sweep the surrounding airspace, the SPY-1 has no moving parts at all. It consists of 4 large fixed antenna arrays, one mounted on each side of the ship's superstructure, facing forward, aft port, and starboard. Together, these 4 arrays provide complete 360-degree coverage of the airspace around the ship simultaneously, with no gaps and no dead zones. Each array contains approximately 4,350 individual transmit-receive modules. Each module can independently transmit and receive radar signals at microwave frequencies. The radar beam is formed electronically by controlling the relative phase of the signal transmitted by each module, a technique called electronic beamforming, or phased array operation. By adjusting the phase relationships between thousands of modules, the radar can steer its beam electronically to any point in the sky within its field of view in microseconds without any mechanical movement. This electronic steering capability gives the SPY-1 a fundamental performance advantage over conventional rotating radars. A conventional mechanically rotating radar can only point its beam in one direction at a time. It sweeps around continuously and updates the position of each target once per rotation, typically every few seconds. The SPY-1 can track hundreds of targets simultaneously by rapidly switching its beam between them, updating each target's position many times per second. It can dedicate tracking beams to specific high-priority threats, while simultaneously scanning the broader airspace for new threats. It can adjust its waveform and signal processing for different types of targets. Fast, low-flying missiles require different tracking parameters than high-altitude aircraft. And it can do all of this automatically without any operator intervention, guided by the Aegis Battle Management Computer, which monitors the tactical picture and allocates radar resources automatically to maintain the best possible track on every contact. The Aegis Battle Management Computer is the brain of the combat system. It receives data from all the ship's sensors: the SPY-1 radar, the hull-mounted sonar, the electronic warfare systems, and external data links from other ships and aircraft, and fuses this information into a single unified tactical picture. It tracks every contact in the surrounding environment, classifies each contact as friendly, neutral, or hostile based on its behavior, flight profile, and IFF transponder responses, and calculates the threat priority of each hostile contact. It then allocates weapons from the ship's inventory to engage the highest priority threats, while managing the available weapons load to ensure the ship retains a defense capability against subsequent threats. This automated threat assessment and weapon allocation process can handle dozens of simultaneous engagements far beyond the capacity of human operators working manually. The Aegis computer can execute a full engagement sequence from threat detection to missile impact in seconds, with the human operator simply authorizing the engagement rather than manually directing every step. The weapons of the Aegis destroyer are delivered primarily through the Mark 41 vertical launch system. The VLS consists of rows of vertical cells embedded flush in the deck of the ship, fore and aft of the superstructure. The Arleigh Burke class carries 90 to 96 VLS cells, depending on the specific variant. Each cell is a sealed launch canister containing a single missile held vertically ready for instant launch. When a launch command is received, the missile ignites and exits the cell vertically. The hot gas from the missile exhaust is deflected downward through a gas management system below the deck, preventing the exhaust from damaging the ship or adjacent cells. The entire sequence from launch command to missile away takes approximately 2 seconds. Multiple cells can be launched in rapid succession. The ship can fire multiple missiles within a single second if required to engage multiple simultaneous threats. Each VLS cell can be loaded with different missile types depending on the mission. The standard missile SM-2 Block 3B is the primary anti-aircraft weapon. It uses semi-active radar homing. The ship's fire control illumination radar illuminates the target with a continuous radar beam, and the missile homes on the radar energy reflected from the target. The SM-2 can engage aircraft and cruise missiles at ranges up to 170 kilometers and at altitudes from just above the wave tops to the upper stratosphere. Multiple SM-2 missiles can be in flight simultaneously, each guided to a different target by the Aegis fire control system. The standard missile SM-6 extends the fleet defense capability significantly. Unlike the SM-2, which requires the ship's own radar to illuminate the target throughout the engagement, the SM-6 has an active radar seeker in its nose. This seeker can home on the target autonomously in the terminal phase of flight. This beyond visual range capability means the SM-6 can engage targets at ranges beyond the horizon, targets that the ship's own radar cannot see, using targeting data provided by other platforms via data link. An airborne early warning aircraft or another ship over the horizon can detect and track a target and provide the targeting data needed for the SM-6 to engage it, even though the launching ship cannot see the target directly. The SM-6 also has a secondary anti-ship capability and, in its most recent variants, a ballistic missile defense capability, allowing it to intercept short and medium-range ballistic missiles in their terminal phase. The Tomahawk cruise missile provides the destroyer's long-range land attack capability. The Tomahawk is a subsonic cruise missile with a range of over 1,600 kilometers in its current variants. It flies at low altitude, typically below 100 meters, following the terrain to avoid radar detection. It uses GPS inertial navigation and a terrain comparison system called TERCOM to navigate with extraordinary precision to its target. In its latest Block 5 variant, the Tomahawk can receive updated targeting data in flight, allowing it to be redirected to a different target after launch, and can strike moving surface targets using a maritime attack mode. The Tomahawk has been used in large numbers in every major American military operation since its introduction in the 1991 Gulf War, demonstrating extraordinary reliability and precision in combat conditions. For close-in defense against missiles that have penetrated all outer layers of the ship's defenses, the destroyer carries the Phalanx close-in weapon system. The Phalanx is a self-contained radar-guided weapon system consisting of a 20mm M61 Vulcan Gatling gun integrated with its own search and tracking radar. The system operates fully autonomously. It searches for incoming threats, tracks them automatically, and opens fire without any human intervention when a threat enters its engagement envelope. The M61 Vulcan can fire at rates of up to 4,500 rounds per minute, firing tungsten or depleted uranium penetrator rounds that destroy incoming missiles through kinetic energy. The Phalanx engagement envelope extends to approximately 1,800 meters. It is the absolute last line of defense. If a missile has reached this range, it has already penetrated every other layer of the ship's air defense. Anti-submarine warfare is one of the destroyer's most operationally important missions. Enemy submarines represent one of the greatest threats to surface ships and to undersea communications cables, and the destroyer is one of the primary platforms for hunting and destroying them. The AN/SQS-53 hull-mounted sonar system in the bow of the ship transmits acoustic pulses and listens for reflections from submarine hulls. It also operates in passive mode, listening for the characteristic sounds produced by submarine machinery and propellers. The AN/SQR-19 towed array sonar is a cable up to several hundred meters long, towed behind the ship, containing hydrophones spaced along its length. The long baseline of the towed array provides sensitivity to very low-frequency sounds that travel great distances through the ocean, giving the destroyer the ability to detect submarines at ranges of tens of kilometers. When a submarine contact is gained, the destroyer can prosecute it with the MH-60R Seahawk helicopter operating from the flight deck at the ship's stern. The Seahawk is one of the most capable anti-submarine helicopters ever built. It carries its own dipping sonar, a sonar transducer lowered into the water on a cable, allowing it to detect and localize submarines at ranges far from the ship. It can drop sonobuoys, small disposable sonar receivers, to establish a wide-area acoustic surveillance picture around a suspected submarine contact. And it carries the Mark 54 lightweight torpedo for attacking submarines once their position has been established with sufficient precision. The Combat Information Center, the CIC, is the nerve center of the destroyer. It is a darkened room deep in the ship's superstructure filled with radar displays, tactical displays, weapons consoles, and communications equipment. During combat operations, the commanding officer and the tactical action officer, the officer with authority to engage targets, work from the CIC rather than the bridge. The CIC gives them complete situational awareness of the tactical environment, the positions and tracks of all contacts, the status of all weapons and sensors, and the communications links to other units in the strike group. Modern CIC systems display all of this information on large-screen tactical displays that give the entire watch team a common operating picture and allow rapid coordination of complex multi-ship engagements. The destroyer represents the current pinnacle of surface warship engineering. It embodies decades of continuous development driven by the relentless evolution of the threat environment. Every system reflects a specific engineering response to a specific threat. The SPY-1 radar answers the saturation missile threat. The VLS provides rapid, flexible weapons employment. The gas turbine propulsion provides speed and maneuverability. The phalanx provides the ultimate backstop. Together, these systems make the Arleigh Burke-class destroyer the most capable and most survivable surface warship ever put to sea. That is how a naval destroyer works. We are Mech Cosmos. Engineering explained. If this video gave you a new appreciation for the most capable surface warship ever built, then subscribe, hit the notification bell, and join us for the next video, because every machine has a story, and we are here to tell it.